Hello, my name is Diego Romeres, and today I'm going to present our model-based reinforcement learning algorithm for controlling robotical systems that we call MC-PILCO. I work done in collaboration between Mitsubishi Electric and the University of Padua, and these are all my great collaborators. So if you're working in control of robotic systems, here we see a few examples. You probably have thought about how to model complex dynamics, how to deal with uncertain propagations, and you are looking at metrics like data efficiency and the generalization to new tasks of the policy that you learn. Our solution to this is based on model-based reinforcement learning, and that follows the classical scheme that was introduced by PILCO a few years ago, where from data we start by learning a model of the system. We try then to optimize a policy to solve a specific task. We test our policy on the real system. We collect some data, and then we keep reiterating this cycle until we converge to a policy that can learn the task. So based on this framework, our MC-PILCO algorithm is a model-based policy gradient algorithm that in the model learning stage uses Gaussian process regression to describe the one step ahead system dynamics. But then, in order to go up beyond the assumption of Gaussianity, during policy learning, we simulate the evolutions of the system using particles. And with these ones, we can estimate the cost functions, and we can compute the kernel by using the parameterization trick. This scheme was then tried in the past, but it was not working in previous literature. So let's try to understand what are our contributions starting from the model learning. So if you think about the Gaussian process regression, usually you think, what is the kernel that I should use? Well, whatever is your choice is, MC-PILCO is a framework that allows you to use any kind of kernel functions, which, for example, was not possible in PILCO. And so we don't have to enter any details, but whether you have a physical model, a black box model, or a model that combines physics and data-driven models, you can write it as a kernel, and you can put it into your MC-PILCO framework. The second contribution was that while classical approaches usually learn one independent Gaussian process for each dimension of the state, what we propose is called speed integrations. And if your state is composed of position and velocity, we will just learn the velocity, and the evolution of the position is given by the integration in time. So we will have to learn half of the Gaussian processes, and we are learning the Gaussian processes in a more physical, consistent manner. After model learning, we are interested in policy learning that has the purpose of minimizing the expected long-term cost function. And how we do it? Well, we already said that we use particles. So this allows us to not have any approximations in structural approximation and distribution of the evolution of the state, and allows any kernel function. As we said, we use the parameterization trick to compute the gradient of it. And what really made us work in this scheme was the introduction of the dropout. That now is not used like in computer vision or deep learning, but you're using it for control. So by dropping off the parameters of the policy, it basically acts as a regularizer that allows us to escape local minima and generalize to new tasks. And also the reshaping cost function was a fundamental characteristic for us. In the paper, we'll see many simulations, but here we report how in only 8 seconds of data, we can learn starting from a poorly tuned PID controller, a trajectory tracking controller for this UR5, by just using a few hundreds of data. But this was not enough when we were trying the algorithm for real-world systems, that we say partially measurable systems, because stay with me here, when we start from a real system and we have the state, position, velocity, usually the sensor gives us only positions. And then we need a fast estimator that complete the states to fit to the policy and control the system. So what we propose is that we should have 2 different estimators. One in the model learning phase that is very accurate to really try to learn the real system. So it could be even be a causal filter. And another one that another estimator that during policy learning corrupts the prediction of the models with something that emulate the state estimator online time, so that the policy is trained with a real condition that it will see during execution. And this turned out to be a successful idea. Here there are a couple of examples, a Furuta pendulum and a ball and plate system. And both were learned with just a few hundred data. And on top, we show with different kernel structures, as we were saying before, black box with some structure. And here we are adding the physics. And in only 9 seconds, we can learn how to swing up the Furuta pendulum. And in the ball and plate, we want to show generalization, because after only 11 seconds, we are able to learn how to stabilize this ball from any condition in the perimeter of the plate. With this, I want to conclude. Here there are just some summaries, and if you're interested in it, please, you can download our code in GitHub. And these are my collaborators. Thanks for your attention.